This is part 12, LLM training workflow of the series AI for Everyone. Here's the typical training process or workflow for LLM. We have four major stages of training, and they are conducted serially. Each stage has its own data set, specifically curated or prepared for that stage. Then there is an algorithm, or a specific training objective, used at each stage to optimize the model. By the end of each stage, you get a model that is further refined in the subsequent stages. The first stage is often referred to as the base model stage. As can be seen in the notes section, this stage consumes the majority of the training time or compute resources. Some estimates suggest it could be as high as 99%, given the extensive hardware requirements. The remaining stages generally focus on refinement or fine-tuning, where the already trained model is adapted or improved for specific tasks or behaviors. So for the first stage, we feed in a large amount of data to train the base model. Remember that high-quality data tends to produce a more capable large language model, LLM. Also, the number of epochs used during training can significantly influence how well the model learns and retains knowledge. More epochs typically mean the model has more opportunities to adjust its parameters and internalize patterns from the dataset. Only the first stage is fully automated, while the remaining stages involve human-in-the-loop processes. The steps that require human involvement are indicated by a human icon. Keep in mind that generative AI is a rapidly evolving field, and processes can change quickly. The steps described here are already nearly a year old. As we have learned, the first step of LLM is to tokenize the input data. It's not always all about size. Even though Meta's Llama has 65 billion parameters compared to GPT-3's 175 billion parameters, Llama is a significantly more powerful model, and that's because it's trained for significantly longer. In this case, 1.4 trillion tokens versus 300 billion tokens. So you shouldn't judge the power of a model just by the number of parameters that it contains. Again, to emphasize how and what you train on matters. Next, we shuffle the data and create batches of the tokens. Here for simplicity, we are showing batch size of 4 rows and context size of 10 tokens. Each row has a row termination token, 50256. Also shown is sample text input for each row and its tokenized representation in batch. Remember from our previous video, the gradients are updated after each batch. As you would also remember, gradient update is iterative process, so it might have to update the gradient many times before it is able to predict correctly. And that is where the most of the time is spent in the training or learning process. Here is the picture of how multiple iteration improve the learning and therefore the quality of output. The stage of supervised fine-tuning, SFT. In this stage, we fine-tune the large language model on a small but high-quality, curated data set consisting of prompt-response pairs. These pairs are typically structured in a question-and-answer format. On the left side, the prompt and its corresponding response are prepared or created by humans, while on the right side, an instruction or system prompt is provided to guide the model's behavior. Models refined through SFT are now capable of functioning as effective assistants and can be deployed. However, they may still benefit from further refinements to enhance their performance and reliability. The next stages are called reinforcement learning from human feedback, or RLHF, which includes both reward modeling and reinforcement learning. In reward modeling, a curated data set of questions, which will be used for prompting LLM, are created by human. Here the algorithm will be of type classification. We take in supervised fine-tuned model, or SFT model, and ask it generate multiple completions for the same prompt. We then ask people to rank these different completions that are generated by LLM. It takes humans really long to grade them and could easily take hours for single prompt output grading. The final step is reinforcement training. Now, once we have the reward model, we can use that to train the SFT or instruct model. Let looks the picture. Here, we first create a copy from SFT or instruct model and call it a policy model. This policy model will be optimized further using reinforcement learning, guided by reward model's score. Next, we prompt the policy model so that it can generate response. For each generated response, we feed the prompt and response pair into the reward model to get a reward score. Each output from the policy model is associated with reward signal derived from human feedback data that it was trained on. Using the proximal policy optimization, or PPO, a policy gradient method. It computes gradients that indicate how the policy model should adjust its parameters to maximize the reward model score. To avoid catastrophic changes in the model's parameters, where the model might diverge from previously learned valuable behaviors, PPO applies clipping or incorporates a KL divergence penalty. Clipping restricts the ratio of the new policy to the old policy within a specific range, ensuring updates are not excessively large. KL divergence penalty, alternatively or additionally, a term is added to the reward function penalizing deviations from the original SFT distribution. This penalty ensures the model remains close to the well-behaved baseline while still improving. We repeat the process of prompting the model, scoring with the reward model, and applying PPO updates until performance converges or the policy meets predefined criteria. Finally, we have a fine-tuned policy model that balances maximizing the reward model's score with maintaining stability and consistency. That completes the LLM training workflow. Remember, LLM is a rapidly evolving field, and many new techniques are being invented to enhance or optimize LLMs. Now let's talk about hallucination, what it is, and why do LLMs hallucinate. One reason is noisy and incomplete training data. LLMs are trained on massive corpora scraped from the internet, which inherently include errors, outdated facts, and even outright falsehoods. Because the training data is not perfectly curated, the model learns patterns that sometimes reflect these inaccuracies. For example, when asked to generate legal citations, an LLM might invent case names or precedents that appear consistent with legal language, even though those cases never existed. In several documented instances, lawyers who used AI tools like ChatGPT for legal research ended up citing fabricated cases in court filings, resulting in sanctions and disciplinary actions. Second is statistical pattern, matching and overgeneralization. LLMs generate text by statistically predicting the next token based on patterns found in their training data. They do not understand content in the human sense. They merely recombine fragments they've seen. This process can lead to overgeneralization, outputting details that fit common language patterns but aren't factually grounded. For example, an LLM might generate a news article that follows a familiar journalistic structure but includes a fabricated quote or event because that style is common in its training data. There have been cases where ChatGPT produced coherent news stories with invented details. It once generated a fictitious report about a political event, echoing a pattern seen in real news but entirely made up. Third is contextual ambiguity and prompt sensitivity. When a prompt is vague or lacks sufficient context, the LLM is forced to fill in the gaps with its own generated content. This creative interpolation can lead to hallucinations, adding details that seem plausible in context but are not based on any verified source. For example, if a user asks for a biography of an obscure historical figure with minimal available information, the model might generate a detailed life story that never actually occurred. Multiple users have reported that when asking ChatGPT for summaries or details about little-known events or figures, it often provides confident yet entirely fabricated narratives. Fourth is decoding strategies and sampling techniques. During generation, LLMs use techniques like temperature sampling and beam search to decide which token to output next. Higher randomness, e.g. high temperature, can lead to more diverse and occasionally more creative outputs, but this also increases the risk of straying from factual accuracy. For example, adjusting the temperature parameter may cause an LLM to produce a short story or explanation that is inventive and entertaining, yet includes details that are completely invented. Experiments have shown that higher temperature settings in models like ChatGPT lead to outputs with greater creativity, but also a higher incidence of factual errors or hallucinations. Fifth is inherent limitations in model architecture. The transformer architecture underlying most LLMs is designed to optimize for fluency and coherence rather than truthfulness. Since these models are essentially sophisticated statistical pattern recognizers, they lack built-in mechanisms to verify facts or check consistency against real-world knowledge. For example, in summarization tasks, an LLM might produce a well-organized summary that includes details not present in the source document. simply because the model expects such details to occur based on its training. There have been reports of AI summarizers that generate summaries of legal or scientific documents with added fabricated details, misleading users about the original content. Sixth is exposure bias and training objective mismatch. LLMs are typically trained using maximum likelihood estimation, MLE, which rewards the model for predicting the most likely continuation of a prompt. This training objective can lead to overconfidence, even when the model is uncertain. As a result, the model may assert false information with high confidence. For example, when generating academic content, an LLM might confidently provide a citation or fact that sounds reasonable but is actually fabricated, because the training process reinforces confident, complete answers. Several academic papers and legal documents have included confidently stated but entirely incorrect information generated by AI, highlighting how the mismatch between training objectives and factual accuracy can have serious real-world implications. In conclusion, LLM hallucinations arise from a confluence of factors, from the quality of training data to the fundamental nature of statistical language modeling and the techniques used during text generation. Understanding these reasons helps researchers and developers devise strategies such as improved data curation, refined decoding methods, and incorporating fact-checking mechanisms to mitigate hallucinations and improve the reliability of AI-generated content. Because of this, human oversight is always encouraged over the outputs generated by LLM. Let us now talk about another drawback of LLMs. Why do LLM have biases? Here are some of the reasons behind why LLMs have biases in their output. One is due to biased training data. LLMs are trained on enormous data sets scraped from the internet. Since these data reflect historical, cultural, and social biases, including stereotypes and skewed representations of gender, race, and ideology, the model learns and later replicates these biases in its outputs. For instance, when generating job recommendation letters or role descriptions, an LLM might disproportionately use language that associates nursing with women and engineering with men. Studies and reports have documented that AI-generated recommendation letters can exhibit gender bias, using stereotypical adjectives or assigning roles based on gender, even when the prompt is neutral. Second is due to overrepresentation of majority culture and underrepresentation of minority voices. The training data for LLMs are often dominated by content from mainstream Western sources. This imbalance causes the models to adopt a narrow worldview that may misrepresent or completely omit minority perspectives and non-Western cultural nuances. For example, when asked about cultural practices, an LLM might default to a Western-centric explanation, even if the query is meant to be open-ended or global. Researchers have observed that LLMs frequently provide biased responses regarding cultural topics, reinforcing dominant narratives while neglecting underrepresented viewpoints. Third can be due to objective misalignment, predicting the next token, not fairness. LLMs are optimized to predict the next word based solely on the statistical likelihood, not to generate factually or ethically correct content. This objective means the model mirrors the biases present in its training data without an inherent mechanism to evaluate fairness. For example, in response to politically charged queries, an LLM might generate text that aligns with dominant political narratives rather than offering balanced perspectives. There have been observations where chatbots, such as earlier versions of ChatGPT, produce politically biased responses that reflect the prevailing narratives in their source data. Fourth could be due to prompt sensitivity and interaction effects. The phrasing or framing of a prompt can inadvertently activate latent biases. When prompts are ambiguous or carry implicit assumptions, the LLM may fill in the blanks with stereotyped or culturally biased content. For example, a prompt asking, "Describe a successful leader," might lead the model to generate a description based on prevailing stereotypes, e.g., male, assertive, and Western traits, rather than a more balanced depiction. Experimental studies in prompt engineering have demonstrated that minor changes in prompt wording can lead to significantly different, often biased responses. Users have noted shifts in tone and content that reflect societal stereotypes when different adjectives or qualifiers are used. Fifth could be due to reinforcement learning from human feedback, RLHF, and annotator bias. When LLMs are fine-tuned using human feedback, RLHF, the personal biases of the annotators or evaluators can be inadvertently incorporated into the model's behavior. Since humans are not free from bias, the feedback they provide can skew the model's responses toward particular ideological or cultural viewpoints. For example, if the majority of annotators favor a specific political ideology, the model might consistently produce outputs that align with that ideology even when neutrality is desired. Some users have reported that AI systems, after RLHF tuning, appear to lean politically one way, suggesting that the human evaluator's subjective judgments are influencing model outputs. Sixth could be due to feedback loops from synthetic data, model collapse. When updated versions of models are trained on outputs, synthetic data, generated by previous versions, existing biases can be amplified over time, a phenomenon sometimes called model collapse. This self-reinforcing loop narrows linguistic diversity and entrenches biased patterns. For example, an LLM repeatedly fine-tuned on its own output might increasingly generate homogeneous, stereotyped language, diminishing nuance and further marginalizing minority representations. Researchers have warned that training on synthetic data can cause a decline in output diversity and increase bias, potentially degrading the model's ability to represent less common or minority perspectives. In conclusion, LLMs can produce biased outputs due to a complex interplay of factors, from the inherent biases in their training data and the objectives they are optimized for, to the influence of prompt phrasing and the subjectivity of human feedback. These issues are not accidental but are deeply rooted in how these models are developed and fine-tuned. Ongoing research continues to explore mitigation strategies, from more balanced data curation to advanced prompt engineering, to reduce bias and improve the fairness and reliability of AI-generated content. In short, remember that LLM models may be biased, it may hallucinate, it may have reasoning errors, it is susceptible to prompt injections, jailbreaks attack, and data poisoning, so use them responsibly and constantly monitor their outputs. Always have human oversight or human in the loop for the output generated by LLM models. Hi, I'm Naunihal Singh Sidhu, a Microsoft certified Azure Solutions Architect with over 25 years of experience in IT, specializing in AI-driven transformation, enterprise architecture, big data solutions, and digital innovation.